Today, we're going to pick up where we left off. So last time, we saw how to relate cross sections and decay rates, the things we can actually measure in the lab, to the matrix elements, M or FSI. This is last time. And we saw these involved an integral over phase space, which is just some process and theory independent kinematical factor, and all the interesting dynamical physics is in the matrix element. And so that's what we're going to learn how to compute over the next few lectures. So it's going to take us several lectures to be able to actually compute this. So what we're going to do today is relate these matrix elements to expectation values of products of fields, in particular time-ordered expectation values. And so basically all of our discussion today is going to be in the Heisenberg picture, where these fields are time-dependent. And so that'll be some major progress. So because, as we'll see tomorrow, we can compute these things by going to the interaction picture. And we can relate our Heisenberg picture fields for interacting theories to basically free fields by going to the interaction picture, because in the interaction picture, all of the time evolution of the operators is just given by the free part of the Hamiltonian. And we've already studied the free theory. So these time-ordered expectation values in the interaction picture are ones we'll be able to compute. By relating them to the simplest time-ordered expectation value you can imagine, the time-ordered expectation value of two fields in the free theory. So I gave this outline before. I'll do it again. It's important to keep in mind where we're going in this calculation. It's a rather long calculation, but as we'll see once we go through it, there are shortcuts we can make to directly relate these matrix elements to these propagators. Okay. So this step here will be the focus of today's lecture. It's the LSE reduction formula. Okay. So the derivation itself should take less than half of the lecture. And then the second half of lecture we'll spend examining and justifying our assumptions. So we'll need to make a number of assumptions to derive it, some of which will be very much in line with what you wrote on this morning's homework about how the one-particle states should behave in the interacting theory, some of which will violate many of your expectations. And so today, so at the start, I'm just going to make some assumptions, some of which might seem reasonable to many of you, some of which won't. And we'll try to justify those assumptions in the second part of lecture. And what we'll find is that, these assumptions might not be true. For a naive theory we write down, there's a procedure we can go through to modify our theory to make these assumptions work. So while they may seem questionable, I'm going to describe in the second part of the lecture a simple procedure that we can do to modify our theory to make these assumptions work. Okay, so So that's where we're going today. And so what assumptions are we going to need to make in order to relate this matrix element that we're interested in computing to these time-ordered expectation values that we have a chance of being able to compute in practice? So make a few assumptions. Our first assumption is that AP dagger in the Heisenberg picture in the interacting theory creates a particle of momentum p at time t. So that means we're going to interpret AP dagger acting on the vacuum at time t as a one-particle state at that time. It's going to be a momentum eigenstate, just like in the free theory. So in a sense, there should be some operator that does that creates a one-particle state at some time, one-particle momentum eigenstate at some time, and we're just giving those a name, calling those AP dagger. And we'll assume that the commutation relations between the creation and annihilation operators, furthermore, is the same as in the free theory. So remember, we're using the relativistic normalization. So we have this 2EP in front of the delta. So in other words, the algebra of the creation and annihilation operators is the same as in the free theory at any fixed time. Now, hopefully, too many objections to these statements so far. Our next assumption is going to be that we act with the field operator on the vacuum state. And so here and above, I'm denoting the vacuum of the interacting theory by omega, and the vacuum of the free theory by 0. So in general, if we change our Hamiltonian, we'll be changing the ground state. So we don't expect that the vacuum state of the free theory and the vacuum state of the interacting theory are the same. If the interaction term is small, in a sense, then we would hope that one would be some perturbation of the other. But we'll see what the relationship is between these two vacua next time when we go to the interaction picture. But important point for now is just that they're different states. Okay, so our next assumption is going to be that this state is a one-particle state. With a form factor, or overlap between the momentum eigenstate and phi acting on the vacuum, it's the same as in the free theory. Okay, so many of you stated that you expected exactly the opposite of that these would not be true in your assignment. So again, we'll defer our justification for later, but we'll just assume these things for now. And so we're going to assume this is a one-particle state at least for t going to plus or minus infinity. But we'll assume this holds for all time.
Does it make any difference if you change the vacuum compared to the homework? I mean, I can see it doesn't, but how come it doesn't?
So I have in no way justified this formula. You should be very skeptical. Why? So in your homework, you derived this in the free theory, where we had an explicit expression for the field operator in terms of the creation and annihilation operators. We knew how the field, we could explicitly solve for the time evolution here. So we could do everything very explicitly in the Klein-Gordon case where there's no interactions and derive this. So in that case, that was not an assumption. That was an output of the theory. I'm just, for now, we'll come back to a justification later. So no part of that derivation carries over to the interacting theory. So the time evolution will be different. The vacuum state will be different. So you should be very skeptical of this formula. Yes.
What do you mean by the state K in that formula? Because now we have creation operators that depend on time, but your state with a particle with momentum K doesn't depend on time? Or
so the state K here, I mean, okay, so this one will be omega a k of t as t goes to plus or minus infinity. This is time dependent. We'll allow that t to be arbitrary.
What do you mean by so one of the things I didn't really understand was one particle state, one. So if you have a number operator or something like this, does that measure all does it count all the number of states in my thing? Or if I use it on my one particle state, it give me some wishy-washy time-dependent number. I don't really get it. Can my one particle state split up into two and then come back to one? Does it have transition amplitudes to two and back to one? Or?
Okay, so physically, of course, we would be very upset if a particle number was conserved in the interacting theory. We'd like to be able to describe things like particle decays, where a one particle state transitions to an n particle state. So what I mean here, so at any fixed time, we can define a number operator that's basically just the same as the number operator in the free theory. If we just replace the free creation and annihilation operators with these time-dependent operators. So at one fixed time, we can do that well-defined. So that number operator will evolve with time, and in general won't be conserved. It won't commute with a Hamiltonian. So in that sense, it won't be conserved, but we can, at fixed time, talk about particle number. So that's what I mean here.
This definition that we say that K is defined as T when T goes to plus minus infinity, but for the fields it's for general T.
Yes.
Then how would we use the commutation relations to derive that formula?
We're not going to derive that. We're going to assume that. I will justify it later.
Okay, but there is no commutation relation for this.
Yes, we're assuming commutation relations at fixed T.
Right.
So in principle, if we knew how to solve the Heisenberg equation of motion, we could determine the time evolution of these field operators. And if we had a relationship between these field operators and these ladder operators, then we could determine the time evolution of the ladder operators. Doing that in practice is very hard, so we're not going to do that. In principle, if you could, for some very special system, then you could go about it that way. But in general, that's going to be too hard to do. So we're going to take a different approach. So these are for now just assumptions. We'll come back to justification later. Okay, so if I assume those things, then so we want phi to be a one-particle state, which means it should be linear in the creation operators. So phi of x should be linear in the creation operators if we want it to be create a one-particle state. So it should have some term like this. And if we want the form factor to take the correct form, then we should have IPX here. And then furthermore, if we want this field to be real, we're forced to add the other term. So the expansion of the field operator in terms of the ladder operator looks very much the same as it did in the free theory, although the justification is completely different. Before we solved the Klein-Gordon equation, so we derived everything. Here we just made some assumptions that things worked pretty much like they did in the free theory, and that tells us that the field operators and creation and annihilation operators should be related in the same way. So the assumptions imply this. Okay. And so the only difference we make those assumptions is in the time dependence of these creation and annihilation operators, which, as I alluded to before, in principle you could solve for by solving the Heisenberg equation of motion, but that's usually too hard to do in practice. Okay. And so as you did in an earlier homework, you can invert this relation. And show that the creation operators can be expressed in terms of the field operators. In the usual way. So that just assumes this, and that the kinetic terms are the same as in the free case. So we're just assuming some interaction terms that are don't involve derivatives of the field. Okay. So you already showed this. Okay, so given those assumptions, what we're going to try to derive is a relationship between the matrix element or some scattering process. And we're going to try to relate that to a time-ordered expectation value of products of fields. And so the simplest case we'll consider for simplicity is 2 to 2 scattering. So 2 initial particles going to 2 final particles. we'll see that it generalizes, procedure generalizes fairly readily. We have a different number of initial or final particles. And so that means we're going to consider our initial state to be a state where in the far past we have two particles with momenta k1 and k2. And to save some writing, I'm just going to write this as a sub 1 instead of k1 and a 2 instead of k2. And similarly, our final state is just we have two particles in the far future with momenta 3 and 4, k3 and k4. So most of the work in deriving the LSE formula is in showing the following identity. So first I'll write it and then I'll justify where it comes from. So it can show, based on our assumptions, that A1 at plus infinity dagger minus A1 at minus infinity is minus I times the integral of ik1 dot x times the Klein-Gordon operator acting on 5x. And this integral is going to show up repeatedly, so I'm going to give it a name. I'm going to call it I1 dagger. So note that in the free theory, if we act with the Klein-Gordon operator on the field operator, we just get 0. That's the Klein-Gordon equation. So we're imagining we're in an interacting theory where we have some extra terms, maybe a phi cubed or phi 4 term in addition to the usual Klein-Gordon terms. So this is not 0. Okay. So where does this come from? It basically just comes from our assumptions. And this will be the longest part of the derivation. So let me give myself a little more space. I can do it in one board. So the difference between the creation operators at plus and minus infinity, well, we can just rewrite that using fundamental theorem of calculus as the integral of the derivative of the time-dependent creation operator. And we know how the creation operator is related to the field operators. So we can just use this expression. And get, well, we've got an integral over time here. In the expression for the creation operator, we've got an integral over space. So we're left with an integral over space-time. And so there, if we expand this out, this gives us 4 terms. Or more. We get several terms. So we get one term where this derivative acts on this e to the I kx, and it multiplies the derivative of the field. That will cancel against the term where the derivative acts on this field, because we got a minus I here and a plus I here. So the only terms that survive are where this derivative acts either on the first term, this phi, or where it acts on the e to the minus I kx, and it's multiplied by that. The other 2 terms cancel. So what we're left with is two derivatives on phi of x, and I and minus I cancel, e k1 squared phi of x. The other 2 terms cancel. And well, we can write ek as k squared plus m squared. And then we can rewrite this k squared times phi as, well, that's the same thing that we'd get if we were acted with 2 derivatives on 2 spatial derivatives on this exponential. We can integrate by parts to move them over to act on the field operator. So we get e squared minus 3 gradient squared plus m squared phi of x, which is, and this is just the Klein-Gordon operator. So that's where that identity comes from. Just a few lines. And so we have here, we can relate the creation and annihilation operators in the far future and the far past to the field operators, which is what we want to do. And so if we just use this identity repeatedly, we can relate these matrix elements that we're interested in to the field operators. And so doing that, I have f si is omega. So we've got our final state is 2 particles A4 and A3. In the future, our initial state has 2 particles A1 and A2. In the far past. And so one thing to note is that the operators here are already in time order. So we can insert a time ordering symbol, and it doesn't change anything. So by the time ordering symbol, I just mean, so this is time ordering time ordering symbol, and it means just put the latest operators to the left. So it means put all of the operators that follow the symbol in time order, starting from the latest ones on the left, and put the earliest ones on the right. So without using any commutation relations. So it just means it's a definition for the order of the operators that follow. So like normal ordering, it's a procedure or it's a prescription for what order the operators that follow should be put in. So we can put this in for free because these operators are already in time order.
Sorry. Is that not just the overlap between the initial and final states? Like there's no S matrix or...
Oh, yes. So I could write things, bring out the time evolution explicitly. So here, sorry, I've been. So we should, if we're working in the Heisenberg picture, we should define our states to all be defined at the same time. So here I've defined my states at 2 different times. I shouldn't have done that. I should have, say, picked the initial time as our reference time. And then I should write this as, this is really S times F. We've time evolved it. There's an S missing here. Or if we pick future infinity as a reference time, we could put the S over there. There's no S.
What are we doing?
Let's choose future infinity as our reference time. Then it's F, and it's the way I wrote it before. So future infinity is the reference time. Okay, so we're almost there. What we can do next is use our identity repeatedly. So our identity says that A1 at minus infinity is equal to A1 dagger at plus infinity minus I1 dagger. Note, I1 dagger is just this long integral. And so, and then we can do the same thing for the annihilation operators. So those will be related. The ones in the far future will be related to the ones in the far past, plus I4. So if we just take the complex conjugate of this equation, we get a similar relation with the annihilation operators. The minus sign comes from the fact that we're starting with the plus infinity in one case and the minus infinity in the other case. Okay, so we can now plug these expressions into here. Well, and we get a lot of terms. So each of these each of these single terms becomes 2. So we've got 2 to the 4 terms, 16 terms. So let's look at a few of them. The first term we'll get will be something like time ordering of A4 this time at minus infinity for use this identity. A3 at minus infinity. A1 at plus infinity, and A2 at plus infinity. So that's the first term. And, well, this term is a simple one to evaluate. It's time ordered. It means we put the latest operators to the left. The latest operators here are these A1 dagger and A2 dagger. So those should be moved over here. But A1 dagger annihilates the vacuum from the bra vacuum. And similarly, A3 and A4 will be moved over here where they annihilate the ket vacuum. So this term goes to 0. And we'll get 14 other terms that involve at least one A1 annihilation operator at minus infinity or creation operator at plus infinity. And the time ordering will, in a similar way as for this term, just bring the annihilation operators over to the ket vacuum or the creation operators over to the bra vacuum. And so any term that contains at least one creation operator at plus infinity or annihilation operator at minus infinity will vanish. So the only term we're left with out of all 16 terms are just the ones that involve only these integral i's. So we have the term that survives is the time-ordered product of I4, I3, I1 dagger, I2 dagger. And as promised, we have a relationship between the matrix element and the field operators, because these i's all involve the field operator. So that's our key result for today's lecture, and let me just write it out explicitly once so we can see some of the features of this formula. It's rather long, but worth doing at least once. What we get here is we've got a bunch of factors of I. So each of these integrals contains a factor of I. Then we've got a product. So we have two initial and two final particles. So I'm writing things out in a way that suggests how you would generalize this if we had more initial or final particles. We have, so here, 4 integrals over spacetime. We have then exponential factors. So we're taking a Fourier transform. So here, lambda j is +1 for initial particles and -1 for final particles. So that just keeps track of the fact that for the initial particles, we've got the daggered version of this equation, which has a minus sign here. If we take the conjugate, we'll flip the sign there. And that's really the difference between the initial and final particles, is that sign. And we've got a Klein-Gordon operator for each of the particles. So my notation here is that dj squared is eta mu nu dx mu j dx nu. Okay. So this is the label that indicates which of the x's this is acting on. This is not this label j is not indicating which component of the space-time position vector we're working with. This is a label of which of the space-time integrals we're doing. So you got this thing, and it's all acting on the time-ordered product of fields, the vacuum expectation value of time-ordered product fields. And again, I'm going to introduce some shorthand notation because we're going to be using this a lot. So here, phi I is phi of xi. And so this is the key result of today's lecture. Let's see. LSC. So what we have to do, if we want to compute matrix elements, is first we have to compute time-ordered expectation value. Then we have to act with a bunch of Klein-Gordon operators and take the Fourier transform. Okay. Integral, yes. Thank you. Vivian.
In this derivation, did we use the last assumption about the form?
The form factor told us that we had an e to the IPX here. The first thing told us it was linear. Second thing told us what the coefficient was. So we really used this version of it. But in your homework, you showed that this plus the fact that pi is phi dot implies this. Any other questions on that? Yes.
Does this work if there's different fields?
Can you speak up? Sorry.
Does this work the same if there's like a couple of different fields?
A bunch of.
It's one phi operator, right?
Yes, this would work if we had several different types of fields. So the only, if we had different types of fields, we'd have different types of fields in our time ordered expectation value. And depending on the type of field, we might have different operators here corresponding to the whatever the free version of that field theory was. So the kinetic terms will look different, or fermion fields, for example. This will be later.
In which sense does our assumption hold if for interaction changes mass?
The mass. If
It's in the KZ report.
Sorry, can you speak up?
The mass is in the K0 part of that formula.
That's right.
If the interaction changes mass, how?
But yes, that is a good point. We will come back to that. I'll have a lot more to say about that on Friday, but that's something to keep in mind here. So we used in this derivation that ek squared is k squared plus m squared. So that makes sense only if m is the physical mass. So that's the physical mass that shows up here. So that's something to keep in mind. I can't. I'll postpone a fuller discussion until Friday. Other questions? Okay. So in the second part of lecture, I'd like to examine some of the assumptions we made. some of which conflicted with what you thought would occur in the interacting theory. Okay, so what did we assume? We assumed that phi acting on 0, acting on the omega, was a one-particle state. So we assumed this is a one-particle state. With a particular form factor, particular overlap with the momentum eigenstates. A phi omega is e to the I beta x. Okay, so let's rephrase these assumptions in a slightly different form that'll make discussing their validity a bit easier. So one thing that a one-particle state should be is it should be orthogonal to the vacuum state. So we in the form of the field operator, when we wrote it in terms of the creation and annihilation operators, up on that board there. Here, we noted that it was linear in the, up here, linear in the creation operators. That's because we wanted it to be a one-particle state. One thing we didn't include was a constant term. So constant term would mean that there's a constant term there, this would be on 0. So we're implicitly assuming that the created one-particle state and that the one-particle states are orthogonal to the vacuum state, zero-particle states. So this will be an easier way to look at part of what we assume. So we were implicitly assuming this. The other thing we're assuming that we can just leave as is the form factor is correct. And the third thing, so this is really a statement that one-particle states are orthogonal to zero-particle states. This is about the normalization of one-particle states. And the other property one-particle states should have, if we're going to call them a one-particle state, that should have some information that it's not a n-particle state with n greater than 1. So 1 and multi-particle states should be distinguishable in some way. So this is a slight rephrasing of the assumptions we made before. So what we're going to do in the second part of lecture is we'll examine each of these in turn. And we'll see that what we're going to find is that, well, in general, if we just add an interaction term, it's going to break the first two assumptions. But there's a rather easy thing we can do to fix it and make it work. And we'll see that the last one is actually automatic. Don't need to do anything. That's where we're going. Okay. So the first thing we want to discuss is what can you say about the vacuum expectation value? So this is the vacuum expectation value of a field being 0 in a general interacting theory. Well, there's not a lot we can if we make no assumptions about the form of our theory that we can say about the vacuum expectation value of the field operator. Basically, the only thing we know is the Lorentz transformation properties of the vacuum state and our field operator. We're assuming phi is a scalar field, and our vacuum is Lorentz invariant and Poincare invariant. So basically, the only thing we know is that we can write our field as e to the I e dot x, I of 0, e to the minus I e dot x, where p mu is h and p, the Hamiltonian and momentum operators. So this is basically a generalized version of the relationship between the Schrodinger and Heisenberg picture. Here we're just doing sort of time evolution. We're doing time and space evolution. So the phi of x should be related to phi of 0 by this expression. And so that tells us that phi, the vacuum expectation value of phi, should be this. But by assumption, the vacuum is translation invariant. So we can also write this like this. And without making any other assumptions, there's not much else we can say about the vacuum expectation value of a field operator. We can basically say that that vacuum expectation value should be related to the value at 0. So this is just a some Lorentz invariant object number. So there is nothing else we can say in general, and in general this will be non-zero, which is different from what we assumed. But there's a very easy thing we can do to try to fix this. We can just redefine our field operator. So if we redefine our field operator and define some new field operator, which is our old field operator minus v, then the vacuum expectation value of our new field operator vanishes. And so, while maybe we can't use the LSE formula in the form I've written it for an arbitrary field operator, but as long as we're willing to do a shift, we can. So we'll just choose to do that shift. And so basically from now on, we're always going to be working with this shifted operator, and so I'll drop the tilde. So we can make this work as long as we're willing to shift our field. Okay, the next thing we assumed was that the form factor e to the I k dot x. Okay, so again, there's not a lot we can say in a general theory. Basically, like before, the only thing we really know is how these objects perform or behave under the Lorentz and Poincare group. So what we can say is that K by omega is K e to the I p dot x phi of 0 to the minus I p dot x, like before. And like before, the vacuum is translation invariant, so we can get rid of this one. Over here, we're assuming that K is a momentum eigenstate. So here we get in e to the I k dot x, K phi of 0 omega. And we can then perform a boost. And there'll be some unitary operator that boosts. We won't need to specify what it is, but let's just say that U is a unitary that boosts from K to 0. And Yang will have more to say about this operator. She takes over and starts discussing fermionic fields. Now we'll just assume that there's some unitary that transforms our states by boost. And we can just insert U inverse U twice, if we like. So this is just the identity, unitary matrix. And this will just be, this is how you'll boost the field operator. So this is a boost of phi of 0 as a scalar. So its boosted version is unchanged. The vacuum is invariant under boosts. So over here we just get omega. And here we can boost, we're going to boost from K to 0. So this, over here we've got the state momentum 0. And so we get the factor we want, we assumed, and some Lorentz invariant number that has to just be a function of the mass. That's the only Lorentz invariant property we have for the for a scalar field. Well, yeah.
Why doesn't the vacuum change under boosts?
That's our assumption, is that the vacuum is Poincare invariant. Just making that assumption. So it seems reasonable, like a reasonable assumption. If there's no particles in the state, then it should be invariant under almost any transformation you can imagine, including space-time symmetries. The particles basically are the things that transform non-trivially. So if there's no particle, it should transform trivially.
But if there's no particles, what's the difference between this and the free vacuum?
Well, so this is the state. You can think about it by analogy with ordinary quantum mechanics. So if you, what I'm calling the vacuum state here is the lowest energy state. So if you add a perturbation to your Hamiltonian, you'll change that state. It'll still be the lowest energy state. So in an interacting theory, the vacuum state is the state with the lowest energy, which means it has no particles. Particles will have some positive energy. and if we're comparing two different theories, then a free theory and an interacting theory, then the states and theories will be different. But the interpretation of those different states could still be the same, because we're talking about different theories. Okay. So again, there's no reason that our assumption is satisfied in a general theory. But if we're wrong just by some Lorentz invariant number, so something that we can basically just absorb into our definition of the field, like we did before. Before we could shift to get rid of the problematic constant. So here, instead of shifting, we can rescale. So if we define phi tilde of x to be some n times phi of x, we can absorb this problematic vector. And so, at least for the first two parts of our assumptions, they're not satisfied by a general theory, but it's rather easy to fix. So as long as we're willing to shift and rescale our field, we can make them work. And so we'll always choose to do that, so we can use the LSE formula in the form that I've written it down. Okay, so it just leaves one more assumption, that one-particle states are in some way different from multi-particle states. So we'll turn to that next. This is going to work a bit differently from these first two cases. Okay. So let's try to determine in what sense multi-particle states are different from single-particle states. So first of all, we need some notation to denote our multi-particle states. And let's denote them by P and sigma. So here P is going to be the total three momentum. And sigma will be all other parameters needed to specify the state. So that will be things like relative momenta. So if we have a two-particle state, in addition to the total three momentum, we also need to specify the relative three momenta. If we were dealing with theories with multiple types of particles, then this could include labels on which type of particle is which. If we're dealing with particles with spin, include spin information as well. So we won't really care about what other information is contained here. There'll be some discrete parameters like particle type labels and some continuous parameters like relative momenta. The one parameter that's going to be particularly relevant for us is the total 3 momentum. Okay. So, like we did before, we examine the overlap of this multi-particle state with our supposed one-particle state. There's not much we can say without assuming anything about the vacuum, except for we can exploit the Lorentz transformation properties. And so if we do this in the same way as before, basically this will transform just like the one-particle state on the top board. So it will be like e to the I e dot x e sigma phi of 0 omega. And there's no reason for this to be 0. Let's just give this a name. Let's call this a sigma of p. And this is generally non-zero. Okay. And so there's no real way to fix this in the same sense as we did before. This is basically infinitely many amplitudes we want to make be 0, but actually we think a little bit harder. We don't really want these to be 0 because we want to be able to describe things like decay of a single particle, where a one-particle state in some sense is decaying to a multi-particle state. So what we really want to be able to distinguish are one and multi-particle states at a fixed time, or more particularly at asymptotic time. So we're imagining our scattering experiments, we're sending in some particles from the far past, and in the far future, we're measuring what we get out of the collision. So one thing we'd like to be able to describe is sending in a single particle, getting lots of particles out in the future. And so what we really care about is are one-particle states in the asymptotic past or future different from multi-particle states in the asymptotic past or future? If we can't distinguish those, then there's no sense in which we can say that a one particle just decayed to several particles. And so in order to make this statement precise, we're going to have to introduce the idea of wave packets. So what we really want to be able to okay, so first let me introduce the wave packet. So we can construct some wave packet. It's a sum and integral over sigma, remember it as discrete and continuous parts. And so we can construct some wave packet here. So this is a multi-particle wave packet. This size some function here. And we also want to be able to construct, this is a multi-particle wave packet. And we can also similarly construct a single particle wave packet. And so we can imagine that f and psi are Gaussians, for instance, but it doesn't really, the precise form won't really matter too much. And the question I want to ask is, we want to at least be able to distinguish multi-particle states from one-particle states in the asymptotic past and future. So we'd be happy as long as this amplitude was 0 at t equals plus or minus infinity. So that would give us some way to distinguish them while still allowing for our transitions between one and multi-particle states. So let's see what we can say about this in a general theory. So let's assume basically nothing more than what we just already assumed. So if we write this out, we have the sum, the integral over sigma, integral over psi star, integral over p3k of f, and a1, it's the same a1 as before. So that's an integral of e to the I k dot x, derivative of d sigma phi of x omega minus p sigma minus p sigma phi of x omega times the derivative e to the minus I k dot x. Okay, that's a long expression, but I haven't done anything more than plug in our definition of the wave packet psi, the wave packet, the single particle wave packet, and plug in the A1 in terms of the field phi, the creation operator and the field relation that we used before. Okay, so that's a rather long expression. So what do we notice? We notice here that this factor A sigma, shows up. So that's what we have here. And that's also what we have here. This is also A sigma. And so the part in the square brackets, then if we just sorry, that should be there should have been e to the IPX times A sigma, not just A sigma. A sigma would just be if there's a 0 here. So we have an e to the I e dot x, e to the I e dot x. So this part, we take the derivative, we just get a p0. And if we take the derivative over here, we get a k0. Okay. And so this is all so that's, we can simplify the part in brackets. And then we've got an exponential. Can use, that's the only dependence on x, is this this exponential dependence on x. So that's an integral we can do. We just get a delta, factors of 2 pi. And then we can do the, say, k integral using this delta. So we can do the x and k integral, leaving us with a single integral. And if we do that, we get and somewhat still a messy expression, but we're almost there. So we've got a whole bunch of factors out front, and the only part we really care about is this exponential. Okay, so big mass and an exponential. It's the only part we care about. And so the reason the exponential is the interesting part is let's think about what P naught and K naught are. So P naught squared is just the energy of the multi-particle state. And so that's, you can write that as P squared plus m squared, where m is the invariant mass of that multi-particle state. And similarly, k squared is going to be p squared, because we've used the delta function to set p equal to k, plus m squared. So this is the mass of the one particle state. And this is the mass of the multi-particle state. And if there's no bound states, then m is greater than 2m. So in the center of mass frame, the least energy that a two-particle state could have is if the two particles are at rest relative to each other. Could have relative kinetic energy, of course. But the fact there's no bound states means we're assuming that there's no negative potential energy. So with those assumptions, m is greater than 2m, which implies that P naught is greater than K naught everywhere in our integration region. So this exponential is going to, and we're interested again in the t goes to plus or minus infinity. We want our one particle states and multi-particle states to be different in the far past and far future. This is saying that so as t goes to plus or minus infinity, this exponential is going to oscillate more and more rapidly. And we'll go to 0, in fact, as t goes to plus or minus infinity. So guaranteed by the Riemann-Lebesgue lemma. So this is exactly what we want. We didn't have to do anything else to our field. This is automatic. Well, we did make this assumption, which could be slightly relaxed, but this was automatic. So what our calculation is saying is that one particle states and multi-particle states spread out differently as t goes to plus or minus infinity, and their overlap goes to 0 in that limit. So in that sense, we can distinguish one particle states and multi-particle states.
Can you explain again why it's important that P naught is greater than K naught?
Well, so if the coefficient of t went to 0, then t going to infinity wouldn't mean that the oscillations became more and more.
You need to have P naught not equal to K naught.
That's right. That's what we need. Yes.
Wouldn't you be able to recover the previous result by setting psi and f to delta functions?
We should be able to. In that case, it's no longer true that D naught is different from
All right.
K naught. Yes.
All of this requires the particle to be massless. The one particle is massive. Sorry.
Massive. Yes. Yes.
So
There are significant complications in the massless case.
same.
Same. Yeah. So in the massless case, there are additional IR divergences. So basically, one way to think about the problem is if you have massless particles, the concept of particle number itself becomes harder to define because you can always, it's impossible to distinguish experimentally between a state and a state with an additional massless zero momentum particle. So you can basically just throw in as many zero momentum massless particles as you like. And so that actually can cause additional divergences in theory, IR divergences, which can be dealt with, but requires somewhat different tools than what we'll talk about in this course. So we're for now, we're going to assume all our particles are massive. Okay, so just to recap in the last few minutes. So let's suppose we wanted to study some theory, which was a perturbation of Klein-Gordon theory. Suppose we're interested in adding this perturbation term. Well, that's a theory we might be interested in studying. But if we want to use the LSE formula as I presented it, this theory will not satisfy the assumptions for general choices of M and G. And so we wanted to do perturbation theory using the techniques we'll develop tomorrow in order to compute the time-ordered expectation values. What we have to do is we have to shift and rescale. And rename. And so the bad idea is to try to do perturbation theory using this theory. The better idea is to instead do perturbation theory for this theory, where we've got a whole bunch of extra coefficients. So not only do we have an extra coefficient in front of each of the terms we wanted, we're forced to add an extra term. If we shift a cubic polynomial, in general, we get a linear term in addition to a quadratic and constant terms. We're ignoring constant terms because we're not interested. They don't involve the field, so they're not interesting for particle scattering. So we get a new term. So in other words, we're forced to renormalize our theory, use the LSE formula in the form that I've written it. And the conditions that the vacuum expectation value of phi vanish and the form factor takes the correct form will impose constraints on these coefficients. And so we'll come back to that. We'll come back to that on Friday. But for the next few lectures, for now, we will assume So keep this problem in the back of your mind, but we're going to ignore it for 2 lectures. So for now, we're going to assume all the zi's are 1, and any new terms we get are 0, which in general is not a consistent thing to do, even though we're going to do it for now. It's in general not consistent. It is consistent at leading order, which is what we're going to be looking at mostly for the next 2 lectures. So this is only consistent at leading order. Okay, so that's, and so we have to do this. We'll put that fact on pause for a couple of lectures, and tomorrow we're going to examine how we can actually compute the object on the right-hand side of the LSE formula. So this will be the subject of tomorrow's lecture. Any questions? Okay, I'll see you tomorrow.